In section 2.7, we're going to look at inverse functions. After studying this section, you should be able to verify inverse functions, find the inverse of a function, use the horizontal line test to determine if a function has an inverse, that's a function, use the graph of a one-to-one function to graph its inverse function, find the inverse of a function, and graph both functions on the same axes. All right, so let's first define what it means for a function to have an inverse. So the table we have here are the top 4 movies to win the most Oscars. So Ben-Hur, which was released in 1960, it won 11 Oscars. Titanic, that was released in 1998, also won 11. The Lord of the Rings, The Return of the King, released in 2003, won 11 Oscars. And West Side Story, released in 1961, won 10 Oscars. And we can use this information to define a function. Remember, a function, we have a set that we call the domain, that's the set of inputs, and a set we call the range, that's the set of outputs. And if it's a function, each element in the domain, the set of inputs, must go to one and only one element in the range, the set of outputs. So the domain here could be these 4 movies, and the range would be the number of Academy Awards each of these films won. Okay, so this is a function. Okay, so we could write this function as a set of ordered pairs. So we could call it f, and f would consist of the ordered pairs Ben-Hur 11, Titanic 11, Lord of the Rings 11, West Side Story 10. So a function can be defined using a set of ordered pairs as long as no first coordinates of our ordered pairs repeat. All elements in the domain can go to only one element in the range. So let's take this function that we've written as a set of ordered pairs, and let's undo f by interchanging the first and second components in each of these ordered pairs. So switching the inputs and outputs of f, we obtain the relation. Undoing f, we get now, so we take the first ordered pair, Ben-Hur 11, and we reverse the components. So we get the ordered pair 11 Ben-Hur. Same for Titanic 11. We reverse the components of the ordered pairs, and we get 11 Titanic. We get 11 Lord of the Rings and 10 West Side Story. So if a function f has a set of ordered pairs x, y, then the changes produced by f can be undone by reversing the components of all the ordered pairs. The resulting relation yx, you see that we interchange the x's and the y's. So the function has a set of ordered pairs xy. The inverse relation has a set of ordered pairs yx. And it may or may not be a function. And in this case, this example, it is not a function. This is not a function because we have 11 in the domain of this function mapping to 3 different elements in the range. 11 maps to Ben-Hur, 11 maps to Titanic, 11 maps to Lord of the Rings. So this inverse is a relation, it's not a function. All right, so let's look at inverse functions. Now let's look at it in terms of writing equations. So here are 2 functions defined by equations. These 2 functions describe situations related to some computer, x, okay? So the first function is f of x equals x minus 300. And the second function, g of x, takes x and adds 300. So function f subtracts, I guess, $300 from the computer's price, and maybe function g adds $300 to the computer's price. So let's see what happens if we compose these 2 functions, or we evaluate f at the output g. So that means we're going to replace the input of f with the output of g. So we have f of x equals x minus 300. We're going to evaluate f at g of x. So we're going to replace the x in the function f with g of x. So f at g of x is g of x minus 300. But g of x is equal to x plus 300. So we get x plus 300 minus 300, and that is equal to x. So g of x undoes what f of x does. And I think you kind of could have looked at that and determined that was true, because the function f subtracts 300, the function g adds 300. So one function is undoing what the other function does. All right. So let's look at this in terms of some tables here. So we have over here on the left a table that represents the original price of a computer, and we're subtracting $300. So we're reducing the price of the computer by $300. So if the computer's price was $1,200, when we input $1,200 into our function f at $1,200 is $1,200 minus 300, which is 900. Now, if we take that 900 and we make that the input of g, which was that we add $300 to it. So if the input is 900 and we add 300, that's 1,200. So these two functions are inverses of each other. And you notice this notation that we're using in this second table, f, and we have an exponent of -1. That doesn't mean the reciprocal. That means the inverse. Remember, function notation's special into itself. So f with an exponent of -1 means the inverse function. So if my function f of x is x minus 300, its inverse function is x plus 300. One function undoes what the other function does. So the inverse does what the function does, right? So let's get a definition. The definition of the inverse of a function. Let f and g be two functions such that if I evaluate f at g of x and I get x for every x in the domain of g, and if I evaluate g at f of x, and that is equal to x for every x in the domain, the function g is the inverse of the function f, and is denoted with this notation f with an exponent of -1, which is read f inverse. Again, that does not mean the reciprocal of f. Function notation is special. So if you have what you know is a function and you have a -1 as the exponent, that means the inverse of that function. Thus, f evaluated at its inverse is x. And the inverse evaluated the function also is x. The inverse undoes what the function does. The function undoes what the inverse does. The domain of f is equal to the range of the inverse, and the range of the function is equal to the domain of the inverse. So what does the inverse do? It interchanges the domain and range. The inputs of a function become the outputs of the inverse. The outputs of a function become the inputs of the inverse. You interchange the domain and range to find the inverse. Just like in our example of the movies, we had that set of ordered pairs. The first components of the set of ordered pairs is its domain. The second components in the set of ordered pairs is its range. We reverse those. We interchange the two components. So we interchange the domain with the range and the range with the domain. When we interchange those two components, that's what we were doing. Okay, so let's show that these two functions are inverses of each other. To be able to show these two functions are inverses of each other, I must evaluate f at g of x and get x. But I also must evaluate g at f of x and get x. So I need to evaluate both of those and see if I get x. If I get x for both of those, then these two functions are inverses of each other. So I'm going to first find f at g of x. So I'm going to evaluate f at g of x. So everywhere in my function where there's an x, I'm going to replace that with g of x. All right, so f evaluated at g of x is 4 times g of x minus 7. But g of x is x plus 7 over 4. So I'm going to make that substitution. Okay, the 4's will cancel. So I get x plus 7 over 1 minus 7, x plus 7 minus 7 is x. So f at g of x is x. All right, now let's evaluate g at f of x. Okay, so wherever I have an x in my function g, I'm going to replace that with an f of x. So I get f of x plus 7 over 4. But f of x is equal to 4x minus 7. Four x minus 7 plus 7 is 4x. 4x divided by 4, the 4's will cancel, and I'll get x. So g at f of x is also equal to x. So these two functions are inverses of each other. Since f at g of x, or f evaluated at the output of g of x, is x, that means they undo each other. And since g at f of x is also equal to x, they undo each other. So these two functions are inverses. You could call g of x f inverse of x. And in doing so, you denote that g is the inverse of x. Okay? So if I evaluate a function at another function's output, and I do both, I evaluate f at g of x and g at f of x, and both of those turn out to be x, the two functions are inverses of each other. Okay, so how do you find the inverse of a function? The definition of the inverse of a function tells us that the domain of f is equal to the range of the inverse and vice versa. That means that if the function f is the set of ordered pairs x, y, then the inverse of f is the set of ordered pairs y, x. To find the inverse of a function, you interchange the domain and range. If a function is defined by an equation, which is normally what we do in algebra, we can obtain the equation for the inverse by interchanging the roles of x and y in the equation in the function f. So if the inverse interchanges the domain and range, it interchanges the x's and y's, then we should be able to take our function and do that, interchange x and y, and find the inverse of that function. Okay, so here's our step-by-step process for finding the inverse of a function. The equation for the inverse of a function f can be found as follows. First of all, replace f of x with y in the equation for f of x. Interchange x and y, and then solve that equation for y. If this equation does not define y as a function of x, the function f does not have an inverse function, and this procedure ends. So when you solve for y, that is not a function, then the inverse is not a function, and you can stop. If this equation does define y as a function of x, the function f has an inverse function. If f has an inverse function, replace y in step 3 with f inverse of x. We can verify our results by showing f evaluated at f inverse of x equals x, and the inverse of f evaluated at f of x is also equal to x. So let's see if we can't find the inverse of this function. So we have f of x equals 2x plus 7. All right, so step 1, we are going to replace f of x with y. And we do know that y and f of x are exactly the same thing, exactly the same number, exactly same value. Okay, so step 2, we're going to interchange x and y. So in my equation, y equals 2x plus 7, where there's a y, I'm going to replace that with an x. And where there's an x, I'm going to replace that with y. So I've interchanged x and y, and that's what the inverse does. The inverse interchanges the domain and range. The domain of a function is the range of the inverse. The range of a function is the domain of the inverse. So we interchange the domain and range, we interchange x and y. Now I'm going to solve this for y. I think I'll actually move up here and do that. So I'm going to subtract 7 from both sides. Get x minus 7 is 2y. Divide both sides by 2. And rewrite it. Okay, so let's pause and take a look at this. Is this a function? And the answer is yes, because for every input x, I output only one y. There's no plus or minus in front of this. So for every x in the domain, I'm going to output exactly one and only one value in the range, one and only one value of y. As a matter of fact, this is a line. It's a linear function. And how do I know this is a linear function? I know that because the exponent on the x is 1. So this is a linear function. So since the inverse is a function, step 4, we can write this as f inverse of x is x minus 7 over 2. So given a function f of x equals 2x plus 7, its inverse is x minus 7 divided by 2. The horizontal line test for inverse functions. So if you want to know if the function that you are given has an inverse that's also a function, you can use the horizontal line test. A function f has an inverse that is a function f inverse if there is no horizontal line that intersects the graph of the function f at more than one point. For example, look at the graph on the right, graph A. This is the graph of one of your 7 standard functions. This is the absolute value function. The absolute value is a function. It passes the vertical line test, so it is a function. However, I can draw a horizontal line through this function and hit the graph of the function in more than one place. Here and here. So its inverse is not a function. So the inverse all right, so let's look at the second graph. And this is a graph that we're going to get very familiar with in chapter 4. We'll talk about that then. It is a function, the graph B, the graph on the right. It is a function. It passes the vertical line test. You could draw an infinite number of vertical lines through the graph of that function and not hit it more than once. Not only that, but its inverse is also a function. Because if I draw a horizontal line through it, I only hit the graph once in one place. So it is a function and its inverse is also a function. So the vertical line test is used to determine if the graph is a function. If you could draw a vertical line through the graph and never hit the graph more than once, it's a function. The horizontal line test is used to determine if the inverse of that function is a function. In part A, that is a function. It's the absolute value function. However, its inverse is not a function because it fails the horizontal line test. The second graph, graph B, is a function. It passes the vertical line test. Its inverse is also a function because it passes the horizontal line test. The graph of F inverse is a reflection of the graph of F about the line y equals x. And this kind of sort of makes sense because what does the inverse do? The inverse interchanges the x's and the y's. It interchanges the domain and range. So it would be taking the x's on one side and reflecting it about that line y equals x. So that's what it does. Okay, so how do you graph the inverse of a function given the graph of the function? Well, what does the inverse do? The inverse interchanges all the components in the ordered pairs. So here we have a graph of a function, and we have 3 points on the graph of this function. The first point that we have over on the left there is -3, -2. The second point that we have going from left to right is -2, 2. And then the third point going to the right is what, 4, 1? So how do we graph the inverse? We graph the inverse by interchanging the x and y components in the ordered pair and then graphing those points. So if my first point is -3, -2, if I interchange those two components, I get -2, -3. That will be a point on the inverse of this function. So let's graph -2, -3. All right, so my next point was -2, 2. The point on the inverse graph would be 2, -2. To find the inverse, we interchange the x's and the y's. We interchange the two components in the ordered pairs. So I would graph 2, -2. And the last ordered pair on the graph of my function was 4, 1. So the point on the inverse would be 1, 4. Better label this 2, -2, and 1, 4. So now if I connect those points, I get the graph of the inverse. And these two lines are reflections of each other about the line y equals x. So if I draw y equals x in here, then we can see that each point are the 2 points are the same distance from that line. So the point -3, 2 and -2, -3 are equal distance from that line. Or the point -2, 2 and the point 2, -2, they're the same distance from that line. So they're reflections of each other about that line. They're mirror images. So the point 1, 4 and the point 4, 1 are the same distance from that line. So that's how you find the equation, the graph of the inverse. Given the function, you just interchange the ordered pairs, the x and y components of the ordered pairs. So you switch x and y and plot those points, and that will give you the graph of the inverse. So there is the graph of the inverse that I graphed over on the left in blue. And if we were to look at the two graphs on the same graph, we would get the graph that we see here on this slide. And that is the end of section 2.7.